Our second example is the knapsack problem, 背包问题. There are two versions of this problem. One is simple and the other one is hard. So let's start from the simple one, the fractional version. We say a knapsack with a capacity M is to be packed. Given n items, each item I has a weight and a profit. And if x sub I is the percentage of the item I being packed, it means that we don't have to take the whole item. We can only take x sub I percent of the item. If we only take part of the item I, then the packed profit will be the total profit times this percentage. And optimal packing is a feasible one. Feasible means what? Means that the total weight of all the packed items is no more than the maximum capacity of the knapsack. Okay, so it's a feasible one with maximum profit. And that is, we're supposed to find the values of those percentages such that the total profit obtains its maximum under the constraints that the total weight is no more than the capacity M. And this X is a percentage, so it's a number between 0 and 1. This is the simple version because it can be solved by a simple greedy algorithm. To apply greedy algorithm to solve this problem, step 1, we must determine what must we do in each stage. We're supposed to solve this problem stage by stage, right? So what is the definition of a stage? That is to pack one item into the knapsack, right? So we pack items one by one into the knapsack. And to be greedy, on which criterion shall we be greedy? Well, say we have three options. One is every time we packed one with the maximum profit, or we packed one with the minimum weight, or we packed one with the maximum profit density. That's the profit for each unit of weight, right? Okay, so which one would you prefer? The third one, right, with the maximum profit density. So for example, say we have three items and the capacity of the knapsack is 20 pounds. Okay, and these are their profits and these are their weights. So what is the solution? I would suggest you to pause the video and try this one. So here's the answer. Did you get it right? So what we're supposed to do is to calculate the profit density for each item, right? This one is the one with the largest density, and its total weight is only 15, less than the capacity 20, and therefore we can pack the whole item in, and therefore this is 1, which means 100%. Okay, pack this one in, and we only have 5 pounds left, right? There's not enough space for any of these two items, but still we compare their profit densities, and this one is 1.5, which is a little bit larger than that one. So we pick up this item, but we cannot pack the whole item into the knapsack because we only have 5 pounds left. It is 10 pounds, and that means we can only pack half of it. So it's 1/2, which is 50% of item 3, and therefore pack in the value 7.5. That's 1/2 of 15, and put them all together, we get 31.5. Okay, that's how we solve this one by a simple greedy method. This is the simple version, and the hard version is the 0-1 version. Means that this percentage x sub I cannot be any number between 0 and 1. It's either 0 or 1. Okay, so that means for each item, we cannot only take part of it. We must take the whole item, either to take it or to abandon it. Okay, and this is NP hard. Now look at one specific example. So suppose we have 5 items and the capacity is 11, and these are their profits and these are their weights. So what about the optimal solution? So pause the video and take a minute, try to figure it out. So this is the optimal solution. Did you get it right? Well, think about the greedy method. If we apply the greedy method, let's be greedy on the profit. If we are greedy on the profit, we should first pack this one, right, with the maximum profit, 28. And its weight is 7. So after packing this one, we will only have 4 pounds left. So there's no way to pack these two, which are the optimal solution actually, right? And next, we can only choose 6, and finally 1. So the greedy solution is this, which is 35. And this result would be the same if we are greedy on the profit density, because 28 over 7, that gives 4, which is the largest density. Still, we're going to pack this one. But once we pack this one, we won't be able to get the optimal solution anymore. So it'll be the same. And what if we are greedy on taking the maximum profit or profit density, whichever is larger? Means that we can first try to be greedy on the maximum profit and then try to be greedy on the profit density and compare the two answers and take the larger one as our final result of this greedy method. And how about this? Well, the approximation ratio is 2. It means that we can only guarantee to pack 1/2 of the optimal solution. Now let's see why. First of all, the largest profit, for example, this 28, must be bounded above by the optimal solution. This is obvious, right? Since packing this one is also a solution, just may not be the optimal solution. So it's smaller than or equal to the optimal solution, right? And the optimal solution must be bounded above by the fractional solution. This is also clear because the fractional problem allows us to pack part of an item, right? If this optimal solution has some space left in the knapsack, we can fill it in by a fraction of some other item. So this is an upper bound, right? Okay, next, we have that the largest profit is bounded above by the greedy solution. Why? Because be greedy means we would compare the maximum profit solution with the profit density solution and take the larger one. So this is certainly an upper bound. And finally, we have this. Well, we know that the greedy solution is certainly smaller than or equal to the optimal solution, but their difference is no more than the largest profit. Why? Please keep in mind that this greedy solution is no smaller than the profit density solution because we're taking the larger one between them, right? Now let's compare the greedy solution with profit density with the solution of the fractional problem. What do we get? With both methods, we are actually packing the same items according to the same greedy criterion, right? The only difference is that this is a 1-0 version. So we can only keep packing until there's no space for the last item, right? And in the fractional problem, the profit of the last fraction must be no more than P max, correct? So if we add P max to the greedy solution, this is guaranteed to be larger than, or at least not smaller than, the fractional solution. And the fractional solution is larger than or equal to the optimal solution. And that's why we have this inequality. Okay, so based on this inequality, let's divide both sides by the greedy solution. And what do we get? We have that this ratio is bounded above by 1 plus Pmax over the greedy solution. And we know that Pmax is less than or equal to the greedy solution, so this ratio is bounded above by 1. So this is bounded above by 2. And that proves that the approximation ratio is just 2. So it seems that greedy is not so good in this case. Is there any other method to solve it? Yes, sure. Let's think in DP, dynamic programming. And there are actually 3 dimensions to construct the solution. One is the set of items. So a subproblem contains a subset of the items, right? Another dimension is the profit, and the third one is the weight. Many people would take the profit as our optimization function and find the recurrence equation for the maximum profit with the first I items and with capacity J, and therefore we have a 2-dimensional array for the profit. And actually, that's not the only way to solve it. We can also take the weight to be our optimization function. Find the recurrence equation for the minimum weight. Okay, let's define W sub I and P be the minimum weight of a collection from 1 to I items for this subproblem, with total profit being exactly P. And here we're assuming that all the profits are integers. And then for each item, we have 3 possible situations. One is that we take this item I. So the current optimal solution would be the weight of this item plus the optimal solution for the subproblems. The subproblem is the problem consisting the items from 1 to I minus 1 and the profit of P minus P sub I, where P sub I is the profit of item I. Okay, that's when we take this I. Or if we don't take it, if we skip it, then the optimal solution would be the same as the optimal solution we obtained for the smaller sized subproblem from 1 to I minus 1 with the same profit P. Or if it's impossible to get to this P, we define that weight to be infinity. So it's impossible to do it. And therefore we have this recurrence equation. All right. When I equals 0, when there's no item considered, this is initialized to be infinity. If P sub I is greater than P, it will be impossible to collect the ith item because this is for exactly P. And therefore we're going to have to skip this one. Okay. And otherwise we just compare the 2 choices and take the smaller one because we want the minimum weight. All right. What about the complexity? Here we have I and P, right? And I goes from 1 to n. And the profit goes from 1 to what? What is the largest profit we can get? The total sum of all the profits, right? Or to relax the upper bound a little bit, we can say the upper bound is n times P max. Suppose that in the worst case, every profit is the same as the largest profit. Okay, so this is the worst case. So the size of I is n and the size of P is n times P max. And therefore, the total time complexity is n squared times P max. Here a question for you. Is this a polynomial algorithm? Does it mean that we have just solved an NP-hard problem in polynomial time? Well, to answer this question, we must be very clear about what polynomial means. Polynomial time means that the runtime as a function of the input size is a polynomial function. Here we see n squared, where n is the size of the item set, right? And therefore n squared is indeed a polynomial. That's all right, but you must be aware that p max is also part of the input, and it is not a constant. The size of this value will affect the runtime, right? So imagine if it is a huge number, it could be even larger than something like 2 to the power n. What if that is the case? So the size of this kind of input is defined to be the code length of this number. That is the number of bits it occupies. So for example, if it takes like d bits, then p max is big O of 2 to the power d. So the complexity is not polynomial, it's exponential. Okay. You may compare this method with the one that takes the profit as the optimization function, and that complexity relates to the capacity m, right, which is again exponential, not polynomial. On the other hand, if n is large and p max, or that capacity m, is small, we can indeed obtain an accurate solution by dp. So this is the case where we can solve some special case of NP-hard problems with an algorithm that is sufficiently fast. So although this is 2 to the power d, but if d is small, it's no big deal, right? But what if p max is really large? For example, say when here n is very small, when we have only 5 items, but these are their profits, where p max is more than something like 28 million, and dp is going to run much slower than exhaustive search, right? Because for exhaustive search, it only takes like 2 to the power n, right? And 2 to the power 5 is only 32, which is much smaller than this p max. All right. So what do? Do exhaustive search? You can be serious, right? Well, one solution is that we can round all profit values up to lie in smaller range. What does it mean? It means this. We can divide everything by a certain number. In this case, like divide every profit by something like 10,000. Okay, so p max is now only like something less than 300, and that will run much faster. However, the solution may no longer be accurate, right? It's proven that the approximation ratio is somehow related to some epsilon, where that epsilon is a kind of precision parameter.